Welcome back, everyone. Get ready for another deep dive. And today's topic might sound a little intimidating at first, but trust me, it's absolutely fascinating. We're talking about convolutional neural networks,
Yeah.
CNNs.
Yeah.
Those things that help Facebook tag your friends in photos or let those self-driving cars spot a pedestrian.
Yeah, exactly. CNNs are basically the superstars of computer vision. They give computers the ability to see, well, not literally, but to interpret images just like we do. And in some cases, they even outperform us.
Okay, hold on. See is a strong word. Computers don't have eyes,
Uh,
right? So how can they possibly see anything?
well, think about it this way. When a computer analyzes an image, it sees a grid of numbers, each representing the color value of a pixel. CNNs then come in and process this data through multiple layers, sort of like a detective examining clues to solve a mystery.
So it's more like a mathematical process than actual seeing, right?
Yeah, right. And the heart of this process is the convolutional layer, which is where the real magic happens. Imagine you have a special magnifying glass that highlights only edges in a picture. That's kind of what a filter or a kernel does in a CNN. It scans the image and looks for these specific patterns, like edges, corners, textures, you name it.
So each filter is like looking for a different feature, sort of how our eyes focus on different details.
Precisely. Each filter performs calculations on the pixels it scans, and that creates what we call a feature map. Basically, it's a map highlighting those features it was searching for. And as you stack more of these convolutional layers, the network starts recognizing increasingly complex patterns. So, the first layer might detect simple edges, then the next layer might use those edges to identify shapes, and eventually the network might even be able to recognize, like, complete objects.
Wow, that's pretty amazing. So it builds its understanding layer by layer, going from these basic lines to recognizing my cat's entire face.
You got it. But wait, there's more. After the convolutional layers do their thing, we have something called pooling layers. Think of it like summarizing a really long chapter in a book. You keep the main points, but make it much shorter. So these pooling layers, they shrink those feature maps down. That makes the network more efficient and less sensitive to those tiny variations in the image.
Ah, okay. So like if I take a picture of my cat from slightly different angles, the pooling layer helps the CNN still recognize that it's the same cat, right?
You're exactly right. And there are a couple of different types of pooling that are commonly used. There's max pooling, which basically keeps the highest value from a section of the feature map. And then there's average pooling, which calculates the average value. Both methods help to reduce the data size, but importantly, they do it without losing the key information.
Okay, so we've got these filters that find the important features, then these pooling layers simplify everything. But how does the CNN actually decide what the image is? Like, how does it know if it's a cat or a dog?
Well, that's where something called fully connected layers come into play. They come in at the very end of the network and take all that summarized information from the previous layers, using it to make the final decision. You can think of it as connecting all the dots to finally solve the puzzle.
So the fully connected layers, they're like the judges, right? They take all the evidence gathered by the other layers and then make the final call.
That's a great analogy. They analyze all those patterns and relationships in the data to figure out exactly what the image represents.
This is so cool. It's really remarkable how we can teach computers to understand the world visually in a way that's similar to how we do it. But I have a feeling there's more to the story than just these layers, right?
You're definitely right about that. We haven't even touched on something called activation functions, which play a crucial role in making CNNs so powerful. They introduce something called nonlinearity into the network, which lets it learn these complex patterns that just wouldn't be possible with only linear calculations.
Nonlinearity. Okay. Can you break that down a bit? Explain it in a way that even I can understand?
Sure. Think of it like adding spices to a recipe. If you're making a dish with only salt and pepper, it might be a little bland, but when you add other spices, you get all that complexity and depth of flavor. That's what activation functions do for CNNs.
Gotcha. So they add a little extra oof to the network, right? Making it more capable of recognizing all those complex patterns.
That's it. And one of the most common activation functions is called ReLU. It basically acts like a switch, activating certain parts of the network based on what it receives as input. This helps the CNN focus on the most relevant features and ignore the unnecessary details.
Okay, I think I'm starting to see the bigger picture here. We've got these convolutional layers that are like magnifying glasses, then pooling layers that summarize everything, and fully connected layers that act as the judges. And it's all spiced up with these activation functions.
Exactly. That's the fundamental structure of a CNN. A whole network of layers working together to make sense of images, and they do it in a way that actually resembles our own visual processing.
This is all so incredibly cool. It's just amazing how we can teach computers to kind of see the world like we do. But I'm curious, why are CNNs considered to be so much better at this image analysis stuff than other techniques? What makes them so special?
Well, one of the biggest things that sets CNNs apart is their ability to extract features from images automatically. You see, in the past, researchers had to manually design those features for computers to recognize, which took forever and often didn't produce very accurate results.
So it's like CNNs are doing all the hard work for us, figuring out what to look for in an image without us having to spell it out for them.
Exactly.
Right.
This automatic feature extraction is a game changer. It not only saves a ton of time and effort, but it also allows CNNs to learn features that we as humans might never have even thought of.
That's incredible. It's like they're unlocking a whole new level of understanding that was hidden before. Are there any other advantages that make them stand out from the crowd?
Absolutely. Another key advantage is their ability to grasp what we call spatial hierarchies. What that means is that CNNs don't just see individual pixels. They understand the relationships between them.
Ah, so they can see the bigger picture, not just the individual dots.
Exactly. They learn how features are arranged in space, just like we do when we recognize objects. For example, think about a cat in a picture. You can still recognize it even if it moves to a different part of the image. Well, CNNs can do the same thing.
So they have a sense of spatial awareness, like they understand how objects relate to each other within the image. Pretty impressive. And I'm assuming all this happens pretty efficiently, right?
You bet. CNNs are surprisingly efficient, especially when you compare them to older methods. Part of this is due to what we call shared weights, where the same filter gets used across the entire image.
So instead of learning different rules for every single part of the image, they can just apply the same rules everywhere.
Exactly. This means the network doesn't have to learn a totally separate set of weights for each location, which makes it much faster and less memory intensive.
So we've got smart, efficient networks that can even learn things we can't directly teach them. No wonder they're so popular. I'm curious, were CNNs always this advanced? Did they just appear out of thin air? Or is there a story behind how they evolved?
Well, just like any groundbreaking technology, CNNs have a pretty fascinating history. They definitely didn't appear overnight. They've been evolving for decades, with each new breakthrough building upon the ones that came before.
Okay, I'm hooked. Let's take a trip down memory lane and see how these incredible networks came to be.
All right, so one of the earliest architectures, Linnet, came about back in the 1990s. It was mainly used for recognizing handwritten digits, like the ones you see on checks.
Ah, so that's how banks started automating check processing. Fascinating.
Exactly. Linnet's success in that area proved that CNNs could outperform traditional algorithms when it came to image recognition. And, it really sparked a wave of research in the field. But the real turning point, the big breakthrough, came in 2012 with AlexNet.
What made AlexNet so special?
Well, AlexNet absolutely dominated the ImageNet competition, a massive image recognition challenge. It won by a landslide.
So it's like the Michael Jordan of CNNs, showing everyone what was possible.
That's a great analogy. AlexNet's win was a huge deal. It demonstrated the incredible power of deep learning and the use of GPUs for training these complex networks. It really put CNNs on the map and led to a huge explosion of research and development in the years that followed.
Wow, what an impact. So we've got the pioneer, Linnet, and then the champion, AlexNet. What came next in this evolutionary journey?
Well, after AlexNet, researchers really started experimenting with different architectures, pushing the limits of what CNNs could do. One notable example is VGGENT, which was known for its simple design and its depth. It used these small 3x3 filters stacked in many, many layers. And this really showed that sometimes deeper networks could produce better results.
So it's like they were building convolutional skyscrapers,
Hmm.
going higher and higher to achieve new levels of accuracy.
Exactly. But as you can imagine, building deeper networks came with its own set of challenges. As the networks got deeper, they started running into what we call the vanishing gradient problem, which basically made it much harder to train them effectively.
So like building a tower so tall that it becomes unstable.
Yeah, that's a good way to think about it. But luckily, researchers came up with a pretty clever solution. They introduced something called residual connections. These connections, which were first introduced in a network called ResNet, really helped to overcome that vanishing gradient issue. And this allowed for the training of even deeper and more powerful networks.
It's like adding support beams to that really tall tower to make it stronger and more stable.
Exactly. ResNet's ability to train really deep networks without sacrificing performance, that was a major breakthrough. And, it really paved the way for even more sophisticated architectures to emerge.
This is incredible. We've come a long way from simple digit recognition to building these incredibly deep, powerful networks. What other innovations did researchers come up with?
Well, another important development was the inception network, which introduced the concept of inception modules. What these modules do is use several convolutional layers in parallel, each with different filter sizes, and this allows them to capture features at multiple scales.
So instead of just looking at the image from one perspective, it's like they're looking at it from many different angles all at the same time.
Exactly. This multi-perspective approach lets inception networks extract more comprehensive information from images, and that leads to even better performance on various tasks.
It's like giving the network multiple pairs of eyes, each with a different focus. This whole journey from Linnet to Inception networks, it's truly mind-blowing.
I know, right? And the journey's definitely not over. The field of CNNs is constantly evolving, and researchers are always pushing those boundaries even further.
This has been fascinating. We've covered the basics of how CNNs work, their amazing evolution over time, and all their key advantages. But now I'm really curious to see what they can actually do out in the real world. What are some ways that these networks are being used to solve problems and create new possibilities?
Well, that's where things get really exciting. The applications of CNNs are incredibly vast, and they're growing every day. We're talking everything from self-driving cars to medical imaging and even in the art world.
Wow, I can't wait to dive into all that. Let's explore the real-world impact of these incredible networks and see how they're changing the world around us.
It really is amazing to think about how much of an impact CNNs are already having, and in so many different areas of our lives.
It's mind-blowing. We've talked about self-driving cars, medical diagnoses, even security systems. It seems like they're popping up everywhere these days. And I bet there are tons of applications we haven't even thought of yet.
Oh, absolutely. And one area where CNNs are really making waves is in the creative arts.
Wait, really? I always thought of CNNs as being, these highly technical, analytical tools. How do they fit into the world of art and creativity?
Well, think about all the image and video editing software out there. Many of the features we use all the time, like automatically enhancing photos or removing something you don't want in the picture, those are powered by CNNs. They can even create entirely new images based on your input.
So those filters on Instagram that make my selfies look amazing, those could be using CNNs behind the scenes.
You got it. And it goes beyond just simple photo editing. CNNs are being used to create those stunning visual effects you see in movies and video games. They're making them more realistic and immersive than ever before.
Wow, that's incredible. So CNNs are helping to blur the lines between what's real and what's digital. That's both exciting and kind of mind-bending at the same time. What other creative applications are out there?
Music generation is another area where things are getting really interesting. CNNs can analyze huge libraries of music and learn those patterns and structures to compose original pieces in different styles.
Hold on, you're telling me that CNNs can write music? That's wild. I wonder if they can write a chart-topping hit song.
It wouldn't surprise me. There are already AI-powered music composition tools out there that use CNNs and other techniques to help musicians create new melodies and harmonies, even entire song structures. And some artists are actually collaborating with AI to see what's possible and push those creative boundaries even further.
That's really cool. It makes you wonder what the future of music will sound like with AI playing a bigger role in the creative process. But let's switch gears for a bit. I'm curious about the challenges involved in actually developing and deploying CNNs. I mean, can't all be smooth sailing, right?
You're absolutely right. There are definitely some hurdles to overcome. And one of the biggest challenges, as we mentioned before, is that they need massive amounts of data. To train a CNN effectively, you need a huge amount of labeled data. And that can be very time-consuming and expensive to collect.
It's like they need tons of practice before they can really perform well out in the real world.
Exactly. And the quality of that data is incredibly important, too. If the data is biased or inaccurate in some way, the CNN will learn those biases, and that could lead to incorrect predictions.
That makes sense. Garbage in, garbage out, as they say. So data collection is a big challenge. What are some other hurdles developers face?
Another big issue is what's often called the black box problem. CNNs can be very complex with millions, even billions of parameters. And often it's really hard to understand exactly how they are arriving at their decisions.
So they might be making these amazing predictions, but we don't always know why or how.
That's right. And this lack of transparency can be a problem. especially in areas where explainability is really important, like in medical diagnosis or with self-driving cars. Imagine a doctor using a CNN to help diagnose a patient. It would be super important to understand why the CNN is recommending a certain treatment.
That makes perfect sense. So explainability is a big one. Are there any other challenges that researchers and developers are dealing with?
Well, computational resources are another significant hurdle. Training and running these complex CNNs, especially for those real-time applications like video analysis or autonomous driving, it can take a lot of processing power and memory.
So even though CNNs are getting more powerful, we still need to make sure they can actually run efficiently on the devices we use every day, like our phones and laptops.
Exactly. There's a constant push to develop more efficient architectures and training methods that can reduce those computational demands without sacrificing that accuracy we're looking for.
It's a constant balancing act between power and efficiency. But it sounds like the potential benefits of CNNs are just too big to ignore, even with these challenges.
Oh, for sure. The advancements in CNNs are really driving innovation across so many different industries. They're helping us to solve these really complex problems, automate tasks, and even create entirely new possibilities that were unimaginable a few years ago.
It's like we're watching a technological revolution unfold right before our very eyes. It's super exciting, but with all this talk about the incredible capabilities of CNNs, it also makes me wonder, are there any downsides, any potential risks we should be thinking about?
That's a great question, and a really important one. As with any powerful technology, CNNs can be used for good or for bad. It's crucial to be aware of the potential downsides. For example, we talked earlier about the issue of data bias. If the data used to train a CNN is biased, the network will inherit those biases, which could lead to unfair or discriminatory outcomes.
That's a serious concern, for sure. It really highlights how important it is to have diverse and representative data sets when we're training these algorithms. What other potential risks are there?
Privacy is another big one. CNNs are increasingly being used in surveillance systems, which raises a lot of questions about how our personal data is being collected, stored, and used. We need to be having open and honest discussions about these issues and make sure that the appropriate safeguards are in place.
It's a bit of a double-edged sword, isn't it? We want to harness the power of these technologies, but we need to be really mindful of those potential risks as well.
That's right. It's all about finding the right balance between innovation and responsibility. We need to make sure that the development and deployment of CNNs are guided by ethical principles and a real commitment to using these technologies for the greater good.
Well said. It's a good reminder that technology itself is neutral. It's how we choose to use it that ultimately determines its impact on society.
Absolutely. And as CNNs become even more powerful and integrated into our lives, these ethical considerations are only going to become more important.
Okay, so we've covered the fascinating world of CNNs. Everything from how they actually work to their mind-blowing applications and even the challenges and risks they present. It's been an amazing journey so far.
I agree. It's incredible to see just how far CNNs have come and how they're continuing to evolve at such a rapid pace.
Now, before we wrap things up, I have one final question for you. We've talked a lot about the technical aspects of CNNs, but I'm curious to get your personal perspective.
I'm happy to share my thoughts.
What is it that excites you the most about the future of CNNs? And on the flip side, what are you most concerned about?
You know, what really excites me is the potential for CNNs to help us solve some of the world's biggest problems. Just imagine using CNNs to develop life-saving medical treatments, or combat climate change, or create more sustainable agricultural practices. The possibilities really are endless.
That's incredibly inspiring. It's a great reminder that technology, when used thoughtfully, can be a powerful force for good. But you mentioned concerns as well.
Yes, as much as I'm excited about the possibilities, I'm also concerned about the potential for misuse. As CNNs become more powerful, it's absolutely crucial that we use them responsibly and ethically. We need to make sure that these technologies benefit everyone and that they don't end up exacerbating existing inequalities.
It's a really important point. We can't just focus on the potential benefits without also considering the potential risks and taking steps to mitigate those risks.
Exactly. It's all about finding that balance between progress and responsibility.
This has been a fantastic deep dive into the world of convolutional neural networks. We've learned so much, and I hope our listeners have too. But before we say goodbye, I want to leave everyone with a final thought. As we've been talking about all these advancements with CNNs and their potential, it's kind of amazing how much they seem to mirror, like, our own brains.
Yeah. You know, that's a really interesting observation. It's actually something that fascinates researchers too, that connection between these artificial neural networks like CNNs and the biological ones we have in our heads.
So you're saying there are similarities between how a CNN processes information and how our brains do it.
There definitely seem to be some parallels. Researchers think that CNNs, although they're simplified models, of course, might actually mimic some aspects of how the visual cortex in our brain works.
It's almost like we're trying to recreate, like, the magic of human vision in a machine.
Yeah, exactly. And the more we learn about CNNs and how they function, the more we might be able to discover about how our own brains work. It's kind of a cool feedback loop, you know?
That is incredible. Makes you wonder, is there like a limit to how closely we can actually replicate the complexity of the human brain with these artificial systems?
Well, that's a big question that scientists and philosophers are still debating. It takes us into those deeper questions about consciousness and what it really means to think. But for now, let's maybe stick to the incredible things we're already doing with CNNs, even without perfectly replicating the human brain.
Right. Good point. We've covered a lot of ground today, from understanding those basic building blocks of CNNs to all those mind-blowing applications and even thinking about some of the ethical stuff. I feel like I've gained a whole new appreciation for these networks.
Me too, absolutely. It's been a really cool journey exploring all this.
So as we start wrapping up this deep dive, I want to leave everyone with a few, I guess, key takeaways that we've sort of uncovered along the way.
Sounds good to me.
First off, we learned that CNNs are totally revolutionizing computer vision and a bunch of other fields by giving machines this new way to, well, see and understand the world.
Right, and they're already powering those self-driving cars, helping doctors with diagnoses, making security systems smarter, and even playing a role in art and music.
And secondly, it's just mind-blowing to think that CNNs are actually inspired by the structure of our own brains. The more we learn about them, the more we might learn about our own thought processes and how we perceive the world, which is pretty cool.
Definitely. It really shows you the incredible complexity and, well, the beauty of both natural and artificial intelligence.
And finally, as we talked about, the development and use of these powerful CNNs, they bring up some important ethical stuff we need to think about. Like, we have to be aware of potential biases, address those privacy concerns, and really consider the impact of these technologies on society as a whole.
Couldn't agree more. It's essential to approach these advancements with a sense of responsibility and make sure they're being used ethically, to benefit humanity.
Absolutely. Well, this has been such an amazing and thought-provoking deep dive into the world of convolutional neural networks. Thanks for joining me on this journey.
It's been a pleasure exploring all of this with you.
And to all our listeners out there, thanks for tuning in to the deep dive. We hope you learned some cool stuff today and that you'll keep exploring this incredible world of AI. Until next time, stay curious.